Podemos começar então?
Podemos.
So hi everyone, welcome to today's seminar. Today we will have Leonardo Ferreira from FURG presenting galaxy evolution in the post-merger regime in unions. So Dr. Leonardo Ferreira is an associate professor at the Universidade Federal do Rio Grande, FURG, where he's leading the creation of Artificial Intelligence and Astrophysics Lab, an initiative funded by the Conhecimento Brasil grant and associated with FURG's Institute of Mathematics, Statistics, and Physics. His research focuses on understand how galaxies evolve across cosmic time, with particular emphasis on the transformational role of galaxy mergers. He combines large-scale cosmological simulations, deep learning, and observations from ground and space-based telescopes to model and interpret the observational signatures of merging galaxies. Dr. Ferreira received his PhD from the University of Nottingham, uh, where he worked under the supervision of Christopher and Ulrich on the evolution of galaxy mergers at high redshift using HST and JWST. During his postdoctoral fellowship at the University of Victoria, he joined the Ultraviolet Near Infrared Optical Northern Survey, or UNIONS, collaboration, where he created MUMMI and an ensemble of vision models designed to identify and characterize galaxy mergers up to redshift Z 0.3. So thank you, Leonardo. When you're ready, the floor is yours. Thank you.
Thank you. Thank you for the invitation. It's a pleasure to be here. I wish I was in person there, maybe in next time. So today I'm going to talk about MUMMI, so the multimodal merger identifier, which is this framework that I developed during my work as a postdoc in Canada, University of Victoria, together in collaboration with Sarah Ellison and her group. And this is a work that I pushing it forward here at FURG with my collaborators here. But what I'm really interested is galaxy mergers and how they shape galaxies and how they change how galaxies evolve. So MUMMI is a collection of models that I'm going to discuss a little bit. But with it, we managed to push the boundary of what can be done with machine learning as well. So usually people use machine learning for classification, to reproduce some process that we already know how to do, but do it quickly. But what I'm interested in is applying the machine learning to do stuff that we are not able to do without machine learning. So in MUMMI, I think achieved that, and I want to share some of the results of that with you today. Let me see if I can go forward. Yeah. So this talk is broken down in three parts. So first, I'm going to talk a little bit of the background on why mergers matter for galaxy evolution, very briefly, where we stand now, right? In part two, I'm going to talk about the models themselves that I've been alluding to. So I'm going to describe the methodology that we developed to study mergers, specifically post-mergers. And then some applications of the MUMMI methods, which comes in part three, which I'm going to share some of the results that we got from using it. So why mergers matter? So mergers shape galaxies and they transform galaxies very rapidly, and they can have a dramatic impact in the galaxy evolution. They can transform morphology. They can increase star formation. They can help mother inwards the black hole in the center of those galaxies. But most of all, they are important piece of the hierarchical growth of the structure in the universe. Without mergers, galaxies that we see in the local universe will not form the way they do. So studying how they transform the galaxies is one of the things that drives my research. One of the things that I'm really interested in, not only in the local universe, but also the distant universe. So they are central to a lot of processes that we study regarding galaxies themselves, right? So there's this picture from Hopkins 2008, which is a simulation approach, but it shows you the importance of the merger to the evolution of a galaxy, right? Here you can read this diagram from Hopkins 2008, from down left to the top left, and then top right, and then top down. And the galaxy evolve in that clockwise like that. So first you have like disks, isolated disks in the universe. They start coalescing together, they form small groups, and they start interacting together. And these eventually they fall on themselves, right? They infall into themselves to form a remnant, a coalesced galaxy. So two or more galaxies can merge together to form a bigger galaxy. And then that can trigger all sorts of processes. So here, some results from the simulation that shows that throughout that sequence, we have star formation there in the middle, that top in the middle, the top plot. So you can see the star formation increases slowly as the galaxies get closer together to coalescence. And they have, there's a peak star formation enhancement once the galaxies coalesce. And in the bottom, you have the luminosity from the accretion disk in the center of the galaxy, and that evolves as well. Similarly, so when there's the first passage of the galaxies get closer together, there is some effect, and then when they coalesce, that effect is very dramatic, and that can foster more star formation that can drive mass into the black hole. The black hole then can result in feedback. And so energy, pressure energy is released in the galaxy, and that can make gas go away, dust go away, and that increase the energy of the galaxy, and then maybe that can shut down star formation. And so it's a mechanism for quenching as well. And eventually the galaxy stops forming stars. So a merger can a major merger event in a galaxy can do all those things. I'm not saying that that's all those effects are 100% tied to mergers, but mergers can do that. So they are essential for the picture of galaxy evolution. But this timeline is impossible to retrieve. At least it was impossible to retrieve in the observation. So this is a simulation result. We would love to get that same timeline, time relative to merger and how those physical processes evolve. We can do something with the pair phase because we can measure the pairs, the distances, and the distances between galaxies are a proxy for how long they are going to merge in the future. But once we get to the post-merger, the coalesced, the remnant, you only have a single galaxy. You might be able to do some dynamical modeling to understand the timescales involved, but it's very difficult to do that in large scale. But one thing that is great nowadays is that the suite of cosmological simulations that we have now are very good, and they are very high resolution and large volumes, which means that we can study the evolution of galaxies in simulations in a way that is very analogous to the observation. So the morphologies of galaxies in simulation nowadays are very similar to morphologies of galaxies in the local universe, in a sense that we can do a similar thing that we do in the observations in the simulations as well. But in the simulations, we have the time domain, right? So here I'm showing you a merger tree in the left. So a merger tree is one of the essential pieces of information that we can extract from a simulation, where we show all the hierarchical assembly of a galaxy. So the final galaxy, the galaxy at redshift 0 is on the top, and then you show all the ramifications of the small galaxies that merge together to form that galaxy. And each node is a merger event, basically. So you can look at a merging event and then look forward, look back, and see how the physical processes, the mass, the star formation, see how they evolve with time. That's how Hopkins did that diagram. So this is more like an idealized simulation of galaxy to galaxy. Here we can do that with a cosmological simulation. We can do that with hundreds and thousands of galaxies. So in the right here, there's is a diagram showing how many galaxies we have with resolved morphologies depending on the simulations. And the simulations that we use and that I used for this work here have thousands of galaxies that are resolved like the galaxies in, similar with similar. I mean, they're analogous. The morphologies are well resolved, that they look like galaxies from ground-based surveys. We are not yet there for space telescopes. Maybe a really high redshift. There are some simulations that do that, but we are really lacking in the intermediate redshift range. But for local universe stuff, we definitely can do that. But as I said, it's great in the simulations. We can look at the time domain, and we can see the galaxy evolve, and we can do predictions for the observations. Um, and the simulations tell us that galaxy mergers can enhance star formation. So new pristine gas is inflows to the galaxies. Maybe the interactions of the dynamical friction can compress the gas, can help trigger more star formation. That can trigger, depending on the configuration, starburst. So a lot of gas is consumed at once, and a lot of stars are formed together, which we call starburst. There's a type of galaxy, starburst galaxies, that just are going through that. The same process can trigger the agent because more gas is funneling inwards, as I said, and then eventually quench the galaxies because of the feedback, or maybe the cessation of the star formation can happen because of the lack of gas, because everything was used up during a starburst event. So that's the picture that we have from the simulation, right? So that's the predictions that we have from the simulations that we would love to look at the observations and confirm those, right? So but we cannot do that directly. So one thing that we can do in the observations, and this talk is the hybrid simulation observations, but we are really trying to make the bridge between the simulations and the observations. So one thing that we can do in the observations is to look at the pair phase. So as galaxies approach, how those physical properties change, how the star formation rates change, etc. We can do that with pair catalogs. So there's this big catalog of pairs from Patton 2011 from SDSS, where we can find we can check each galaxy in the sample and see how many companions they have. We can see the velocities, relative velocities, and if they are a specific projected separation, say up to 100 kiloparsec, and we do a velocity cut, we can kind of guarantee that they are going to fall into each other. So we know how they are interacting. So they are not just projected in the sky; they are also confirmed to be at the right redshift to be interacting, right? So there's a lot of galaxies in those catalogs, and we can track the evolution of the mergers in the pair phase by tracking pairs at decreasing separation, and then look at as a statistical sample, look at those properties, how they evolve. So there's if you look at in the simulations how the separation evolve with time, it depends on the mass and the mass ratio of the mergers. But there's a rough translation of 50 kiloparsec equals to 1 gigayear in general. So you have so the separation is a proxy for time, right? So and then we can track that process over time. We can take a sample, separate it in bins of separation, and then measure those properties. So here in the left is this star formation enhancement. So we take out the sample, compare to a control sample, and then see how much the mergers are elevated compared to the non-mergers. And as we see, this plot is, you have to read it, it's the opposite, right? So it's the time is passing from right to left. So the separation is decreasing from right to left. So as the RP there decreases, it means that the galaxies are getting closer together. So in the left here, you can see that as they are getting close together, um, we see the star formation enhancement increasing. And after zero is the post-merger. So the post-merger, I didn't talk a little bit, I didn't talk how we actually study them yet. I'm going to do that. But essentially here, for the sake of these plots, what they do is they classify by eye. If the galaxy look like they just coalesced, you classify by eye. That is the post-merger. And if you do that, the peak of those enhancements usually lie in the post-merger phase, but it's like a steady increase. In the right is the same, but for AGN, here's the optical excess of AGN. As we decrease the distance, the separation, there's an increase of incidence of AGN in close pairs. And the peak is it's missing the labels there, sorry about that. But it's the same axis of the left plot. The peak AGN activity is in the post-merger phase. The same can be done for quenching. So we can find post-starburst galaxies in those samples. Post-starburst galaxies are galaxies that just had a starburst event. So they form a lot of stars, but they are not forming stars anymore. So they are in process of quenching, and you can classify those galaxies through their spectra. But if you do that with the projected separation as well, we see that there's no evidence of incidence of post-starburst in the pair phase, unless you are in the very close for the coalescence, but the statistics are not good. But once you go to the post-merger phase, there's a peak as well. So post-starbursts have a lot of more incidence in post-mergers. But the problem is that once we go back to the Hopkins figure, we can separate the pairs in the sort of the time scale by the pair separation, but we cannot do that for post-mergers. We cannot assign a time scale to the post-mergers. Every study that has been just averaging all the post-mergers together. So we cannot see that transition there, where if there's a fall off of the effect. So as we expect from the simulation, as time goes by, those effects should decrease or change over time. So we would like to measure that. Since then, currently, that was not possible. So enters the UNIONS, as I mentioned in the beginning. So UNIONS is imaging survey of the Northern Hemisphere. It's actually a consortium of different instruments. So the Canada France Hawaii telescope, the Pan-STARRS, and also the Subaru. So each instrument measures images different wavelengths. So the Canada France Hawaii, which is the one that I'm interested in here, the one that I'm going to use the data for, is the R band for UNIONS. So when I say UNIONS R band is imaged with CFHT, and CFHT is very nice quality. It is very good for merger studies because it can go very deep, and it has this low surface brightness mode where it stacks really quickly the observations and can produce very deep imaging fast. So it's very good for surveys of faint structure around galaxies. So in the left here, there are some examples of SDSS galaxies compared to UNIONS R band. You can see tidal structure and things that are not really easy to see in the SDSS imaging. So if the UNIONS survey in the airborne is a huge area in the northern sky, the pixel scale is very nice, and the seeing is very good as well. It's usually 0.7. So it's very good imaging for ground-based telescopes as ground-based telescopes go. It is similar to what LSST is. Image quality is similar to LSST. So anything that you are planning to do with LSST, you can do with UNIONS now, and the UNIONS imaging is going to be public very soon. So if you are working LSST, I know a lot of people in Brazil is very excited about it. I am very excited about it. But if you want to test your methods, have a look at UNIONS. You're probably going to be able to apply that to there. There's there's no time component like LSST, but for raw image quality resolution, it's very analogous. It's very deep as well. It's similar to the depth that LSST is going to achieve in a couple of years. Okay. And the good thing about UNIONS is that it has a very good overlap with SDSS. So here's the footprint from UNIONS and the footprint from SDSS. So CFIS and UNIONS is the same thing. So why that is important? We want to have spectroscopic redshifts to study. We want to have spectra to have the star formation rates, the stellar masses with certainty. So there's a lot of coverage there. So there's a lot of galaxies, 200 to 230,000 galaxies with spec Zs, which is very good. So we can use the very good imaging from UNIONS with the spectra from SDSS and combine those two. And we have a lot of auxiliary data to study mergers. Okay. Another thing is that I wanted to mention briefly is that we did a lot of tests. So this is from Bickley 2024. We did a lot of tests about how well we can retrieve classify mergers in several imaging surveys. And that's like a big important piece of information that you have to have. So a lot of methods of finding mergers from the past decade or so, say CAS, Gini, M20, etc., they are very incomplete. Usually they can be very pure for the most obvious cases, but usually they are very incomplete. So since we started using machine learning and deep learning to classify galaxies, that kind of like solved a little bit of the problem. But still, we want to know how good a survey is for galaxy mergers. And we did a lot of those tests, and we compared SDSS, DECO's, UNIONS, which is CFIS, the high supreme can, and also LSST here, LSST for after the 10 years stacks. And what we find is that UNIONS is usually the sweet spot. LSST is going to be better when the 10-year stacks are in. But currently, the best imaging that we have from ground-based data as a survey is UNIONS. So for retrieving merger, for the completeness and the purity of our samples, CFIS is the best, is the way to go. So as you can see, Sloan, which is a lot of merger studies are done in Sloan, the purity falls off very rapidly with Redshift, and the completeness is below 80%. So since we have access to UNIONS, we use UNIONS because that's the most pristine that we can get for merger studies. And I've been alluding to machine learning. So since 2021, finding post mergers got solved, I would say, in the way that finding obvious post mergers got solved with machine learning. So it's a lot better than visual classification. Nobody can agree on properly on when classifying mergers. And the way it was solved was by producing data from cosmological simulations and training models on the mock images. And that way we have the objective way of saying which galaxy is a merger. It's not a subjective visual cue classification. It's based on the physics, on the appearance and the labels from the simulations. So basically 2021, they did just that. They produced a very big sample of images from the Illustris TNG, and then train a model and then apply to real data and find a lot of new mergers. Here in this work, they focus on the right after coalescent mergers, the most obvious cases, and they achieve very good performance, 80%, 90%, 85%. But I think that's the way to go for mergers because it's very subjective matter. Once you move a little bit away from the most obvious mergers, it gets really tricky. Nobody can agree on if a galaxy is a merger or not. So you end up missing a lot of mergers. I think that's the problem. So you might end up with a very pure sample, but you cannot very complete sample. Right? So this is approach that kind of is a cornerstone of finding mergers, post mergers specifically. So here enters my work, the MUMMI, which is IMU. The U, the first U should be capitalized. Multimodal merger identifier, which is a symbol of mergers of models that I train to not only classify post mergers but also go further. So it's a staged as a hybrid model and is an ensemble, so it's a collection of models. It's a hybrid because I'm not only using CNNs, but I'm also using vision transformers. So I use CNNs and vision transformers. I'm not going to go into the weeds of the machine learning part. I think you probably hear this every time. If you want to discuss the specifics, the methodology behind the networks, and etc., you can drop me an email. I'll be happy to discuss. But MUMMI, as a framework, is a three-stage pipeline where we have stage one, a collection of 20 models, 10 CNNs, 10 vision transformers. I train the models in images from the Illustris TNG. And then we have the stage two where we look only at those galaxies classified as mergers and try to define if they are a post-merger or a pair. And then finally, the third stage, the timescale. For the post-mergers, then we try to classify them in timescale bins. And this is where it comes the novel part of this work. Here it's saying we 84 models, but it's actually 42. That's wrong. But it's an ensemble of models, so it's a lot of models working together. They are trained in slight different subsets of the data set. I'm going to talk a little bit about that. But in this essence is that you have very diverse pool of models trying to classify a galaxy as a merger, and then you use those votes or those probabilities to define a very pure, very complete sample. But this is the machine learning part is great, is okay, but the machine learning is only as good as your data. So I think the good thing about MUMMI is it's grounded in very good training data, which is MegaMock CFIS TNG, which is a new data set that we created. We have to share with anyone that who like to do something similar. So MegaMock CFIS is basically, we took all the galaxies in Illustris TNG 100, all the galaxies that are above 10 to the 10 solar masses, and we produce 80 images of each of those galaxies. So there's roughly 300K unique galaxies in Illustris TNG above the mass range. For each one of those, we made a mock image in 4 different orientations. So we see the same galaxy in different viewing angles, and then in 20 different redshifts. So we have the same galaxy in 80 different visualizations. And for each one of them, we put them in a real background from unions. So what you end up is a like huge sample of galaxies that you can use for training, and all those galaxies have labels. So in the end, megamach CFIS is 24 million images. It's around 12 terabytes of data, so it's a lot of data. But it reproduces very well all the quirks of unions, so all the artifacts, the missing data. You can see some images there with artifacts. But that's very good for the models to generalize those problems and learn that that's part of the data. So we focus a lot of our efforts in producing these data sets. So then, because we have all the galaxies from the illustrators, we can just select them, and we have the mocks, so we don't need to worry reproduce the mocks every time we do a new selection. So then we do just that. We take megamach CFIS, we do some selections there. So basically, for each stage, we have a subsample of all the galaxies, and we select the mergers. For stage one, we select all the mergers that are eligible above the certain mass range. But we select as well control galaxies that have the same redshift, same stellar mass, same gas fraction, because we want to have a sample of control galaxies that are very similar to the mergers, but are not mergers. And we can do that. And then we train in that balanced data set. So for stage one, we do that for all mergers. Stage two, we do that for only mergers. So we separate them in pairs and post mergers. And then stage three, we do that for the timescales that I'm going to discuss shortly. Right, so stage one, briefly, what we do is we take 6 million images of megamach CFIS, and then we break that down in small training sets of 100K images. And then we train a pair of models, each on one of the subsets. So we have a CNN and a vision transformer for each one of those subsets. So that's why we have 20. It's because we train a CNN and vision transformer in each one of those subsamples, which that means that each pair of models in our ensemble is trained on a different subset of images. So they are diverse in that way. They don't see the same images. And as you can see in the right here is some of the performance metrics. It beats the Bickley 2021 work at the short time scales. But also it can classify galaxies up to 2 gigayear almost. So we can achieve the same performance as Bickley, but up to 1 gigayear or so. It then falls off a little bit, but not as much. You can see that it's capped at 70%. So which means after we train MUMMI, the stage one, we realized that, okay, MUMMI is actually being able to pick up those long timescale mergers, post mergers, and that's very good for that initial problem that I outlined with the Hopkins panorama. And this plot shows that. So here is, so we can do two different selections, right? We can do simple majority. So from all the 20 models in stage one, we can select only those galaxies that are classified as mergers by the majority, so 11. Or we can also select only the galaxies that were unanimously classified by all the models. And that's a little bit different in each case. So in one case, you have like a higher completeness, as you can see by the orange. But the purity is kind of flat, so that's good. But if you use the unanimous votes, you can get purities of almost 95% up to 2 gigayears. So which is very compelling, and we got very excited when we saw this result. The completeness falls off, of course, but you're never going to find those mergers with CAS, for example, at 2 gigayears because the morphology is very subtle. I'm going to show some images, but it gets very hard to classify those long tail mergers. So that's how we use stage one. Stage two is very simple, actually. It's just two models because the problem is very simple. Is a pair or not? A merger being a pair is very obvious in the cutout in the stump. So we just train two models and that achieves 95, 96%. Same thing, very similar to stage one, but just one with one sample instead of 10. And one thing that we can do, as I've been saying, we would like to combine simulations with observations. So after we train MUMMI stage one, stage two, we can, instead of classify the galaxies, we can pass all the images to the networks, and then from the features extracted by the networks, we can create these representation spaces where we represent galaxies in this U map, in this by the two-dimensional space. And here I'm showing you in the right this representation for the observations, and in the left these representations for the simulations, and they are mirror, but just for a stylistic choice, but they are the same distribution of points. The regions mean the same thing. So in orange are the post mergers, the teal is the pairs, and you can see that those regions are where the mergers are. You cannot see properly here in the bottom, but the bottom you have the spirals, and the top you have the ellipticals. So the mergers are in the middle between the spirals and the ellipticals, which makes physical sense, as we know that spirals merging together can form ellipticals. So there is some physical meaning in this representation space produced by MUMMI. But not only that, we can use this representation space to actually communicate between the simulations and the observations. So if we select spirals here in the observations, we know that spirals are there. So if we go to that same region of the simulations, we can find the spirals of the simulation, and so on so forth. So if there's a lot of nuance here. There's, for example, here in the region below the merger here, there's bars and rings and etc. You can also, MUMMI also picks that, so it's very good at picking very subtle morphological cues. So MUMMI not only is a good classifier of mergers, it has also a very good bridge between the simulations and the observations. Here's some examples. So we applied that stage one and stage two to unions. And we found 42,000 mergers. So here's some post mergers, as you can see, which was the cover of the talk. From those 42, 13,000 are 20-volt classifications or unanimous. So all the 20 models agree, and they are very good. In all our tests, every time that we're looking at visually at the images, we're like, okay, this is doing a pretty good job. In the area of Bickley 2021, we will classify the mergers and then look at the image to see if there's anything weird, because sometimes there was very obvious no mergers in the samples, but with MUMMI that's very rare. Usually we're very pretty satisfied with the resulting samples. Here post mergers examples, here pairs, and MUMMI is also very good at separating what's a pair and what's the projected pair. Usually the pairs class, you can look at them and they are actually interacting. You have like tidal tails, etc. It's not like just two galaxies that they might not be interacting. Usually they are very, very convincingly interacting. Okay, and that's basically reproducing Biblically 2021, but pushing a little bit further. But what we really want to do is time since coalescence. Can we, using a framework like that, because we have the simulation data as a training data, can we then classify galaxies, the post mergers in the time sequence? And that's what we are trying to do with stage three. Basically, what we do is we take the same galaxy in the simulation and we break down then by snapshot. So a snapshot in the simulation is basically a point in time of the simulation where the data is stored. In illustrious CNG, that means between snapshots, 150 mega years, million years passed. So each snapshot is basically a delta t of 150 million years. So what we attempt to do was labeling the data in this sequence, can we classify the galaxies in this sequence? Can we retrieve the individual snapshots? And if you do that, you can convert that to a timescale. We try to do a regression, but because there's no boundaries between the classes and it is a lot harder to solve. So we decided, oh, let's simplify the problem. Let's do a classification instead of a regression. And what we did, we classify with 10 snapshots. So that means roughly 1.75 gigayears, almost 2 gigayears of time since merger. So snapshot 0, it means that it just merged, just coalesced. Snapshot 10 means that it has passed 2 gigayears since the merging event. And once we do that, we are not able to actually measure the individual snapshots, but if we combine them in a clever way, we can actually do a classification problem that is tractable. So what we've done is, first snapshot is a class. The following two snapshots is a different class. So it's instead of 100 megayears, now it's 300 megayears. The next class is 3 snapshots, and then it's a little bit longer time bin. And then the last one is almost a gigayear, so from 1 gigayear to 2 gigayears. If we do that, if we organize our data like that, we are able to retrieve the time bins with 70%, 70 to 80% accuracy. And additionally, one thing that is really interesting is that for the case, so in this confusion matrix, the diagonal shows you the performance. The off diagonal is the misclassifications, right? The good thing is for the misclassifications, usually if you misclassify a galaxy that is snapshot 0 right after the coalescence, usually you're not misclassifying it as a long time scale. You're classifying in the adjacent bin. So even when things go wrong, they go wrong in a way that makes sense temporally. So we're not really catastrophically wrong. As you can see that the off diagonal, close to diagonal bins are the ones that have more misclassifications. So yeah, so in stage 3, we were able to estimate time since merger. So for post mergers now with MUMMI, we can, once it got classified as a post merger, we run through stage 3. Stage 3 gives us a time scale. Is right after coalescence. Is it recent, meaning up to 500 megayears after coalescence? Then 500 to 1 gigayear, and then 1 gigayear to 1.75 2 gigayears. And we can do that now with MUMMI. Here are some examples of galaxies in each bin. So each row is a different time bin. The first bin is very obvious. You can see that the galaxies look that they are just falling into each other. They just coalesce the cores. In some cases, maybe the core is not 100% coalesced, but they are coalesced as there's no 2 clear galaxies anymore. The second one, you can see those big shells or the tidal features more cleanly. The third bin is a little bit more difficult to tell, but you can still see features, some shells around it, some tidal features that are fading. And the fourth time bin is very subtle, but usually in some cases you can tell that it's a merger, but usually those clear indicators are really fade out. So you can see that there's like a transition between the classes, right? So now it comes to the part that I wanted to share with you, which is the science that comes from having a model like that. So going back to Hopkins, as I show you the pairs phase, we can study. We can study 5 minutes. Okay, we can study with the pairs with the pair separation, and the post mergers. Now we can study with MUMMI. We can separate those galaxies in 4 time bins and see if we see this diagram. We did that for star formation rates. I'm going to go quickly over the results. So here are 4 galaxies that are real galaxies from UNIONS. So they are not the same galaxy evolving through time. They are 4 different galaxies with different time scales. and we select star-forming galaxies from the observations and separate them in the time bins. If we join together the pair phase and the post-merger phase now, we can see this diagram, which is the timeline of the merging, the star formation rates evolving through time. And we can see that the star formation rate peaks at the coalescence, right after the coalescence, but it shuts off in 500 megayears. So this is the first time that we can separate that time scale in the post-merger regime and see that there's different post-mergers and they are different populations and they have different properties. But we can go further. We can integrate that curve now and see how much mass is formed because of the merger. So we found that mergers add 10 to 20% stellar mass just because of this enhancement. So this is not ex situ mass that falls into the main galaxy. This is mass that is added to the galaxies as a sample, as a statistical sample. This is mass that is added just because of the enhancements. So galaxies can grow their mass by 10 to 20% just because of this enhancement of the interacting phase. So it's like a merger-driven mass growth that we cannot pinpoint before because we didn't have the full sequence. If we look at quenching starts right a little bit after the time scale, the coalescence, so around 300 megayears, and that kind of ties down with this star formation enhancements as well. But it falls off really quickly. There's no pair stage excess of quenching, but you can see that timeline now with the time scales in quenching. We can do that for AGN as well. AGN peaks right after the coalescence. It's a long-lived process. It goes down almost down to up to 1 gig a year, but it peaks and it stays a little bit up to 1 gig a year. So excess of agents in post mergers. And finally, if we look at manga data and we separate the post mergers and mergers and we look only at those galaxies that are already quenched with long time scales, we see that, and compared to control galaxies, we see that the mergers, and we match in redshift, stellar mass, and all that, we see that the post mergers after 2 gig years have a structural difference. They are more concentrated, so they have almost 20% more mass in the center than they have in the outskirts. So that's something that we can also do with MUMMI. But basically, sorry to rush a little bit at the end. But if you want to discuss more in detail, let me know. Send me an email. I'll be happy to discuss. I'll take questions if you have them.
Obrigada, Leonardo. So do we have questions? If not, I'll start with one. Okay, I'll start with one and then I pass it on to Alan. Do we have more? Horacio? Okay, so my question is, you talked about many possibilities of the way the mergers look and what the tails and many things. Do you manage to get some sort of clumpy star formation that is happening through MUMMI? I don't know if that is possible with the Illustris TNG 100 or if there's other prospects for that, for clumpiness. The clumpiness that's in mergers.
Yeah, so that's a good question. We never looked at that specifically because I think one of the things that we are limited with Illustris TNG 100 is the resolution. So I don't think we can resolve very well the clumps, and that's why we cut our data above 10 to the 10 solar masses. So to go down under that, we are looking at using TNG 50 and doing the same process to push to lower masses. That's I think answers Rodrigo's question as well. So the mass limit is imposed by the simulation, and I think we cannot resolve a clear knots clumps.
Rodrigo, do you want to ask your question? We don't know about it.
Hey, can you hear me?
Yes.
Sorry, I don't know if my internet is good enough, but I think already answered. It's about the identification of post-mergers at lower masses. Like if you tested the pipeline trained for higher masses in lower masses at unions. So if you could,
So
even though
we
you
test.
didn't train it for lower masses.
We tested, and we can definitely retrieve mergers. We can look at the images, and they're lower masses, but they look like mergers. That's okay. And the performance kind of doesn't degrade as quickly as you expect for lower masses. But because there's that training data cutoff, we decided to, in our science papers so far, let's limit ourselves to the training domain. And for the next generation of MUMMI models, we're going to train with TNG50, which means that we're going to be able to go as low as 10 to the 9.
Okay, we have a question from Alan.
So I'm wondering about post-mergers after they are already quiescent. If in some cases you see these galaxies showing like massive and relatively large disks, or are they mainly just a spheroid?
So the question is if in the long time scale, if they are just spheroids, or if I see the diversity. Is that correct?
Yeah.
I mean, we see diversity. We didn't quantify that. There's a paper that I'm working on, which is going to be in the morphology of the samples. So currently, what we did is we traced star formation rates, we traced starburst, AGN, quenching, and we traced the distribution of the mass in the radii. Morphology is the next big thing. That's one of the things that we are going to explore, how the populations change with time. So the majority looks more spheroid than disks, but the telling tale here is usually the post mergers, they have like they are more concentrated in general. So even if they are like a big disk, there is going to be a disk with like a big bulge.
Thank you.
Horácio?
Okay, done.
Let's try very loud. Be careful to not fall. Aqui.
Oi, Leonardo, tudo bom?
Oi, Horácio, tudo bem?
A tua palestra. Há alguns probleminhas de áudio, né?
Ele não sabe.
Okay.
Passou bons bocados aqui.
My question is following. How good is your definition, or should your definition of coalescence actually? Is there a period of coalescence, or you can define with which precision? Is it the dynamical coalescence, morphological coalescence? What is coalescence actually?
That's a very good question. It is defined by the time resolution of the simulation, which means that what defines coalescence in our case is the merger tree. If there's two galaxies in the merger tree at one snapshot, and there's one galaxy in the next snapshot, we define that's where where the event occur, when the two galaxies merge together to become one in the merger tree. We do a lot of tests with the mass ratio because there's some numerical stripping that happens in the simulations. So we define a mass ratio at some certain time, but what actually limits our precision is the simulation itself, which is, so we cannot go as lower than 150 megayears. So if the merger happens under that window, we cannot say if it's 50 megayears or 100 megayears. For us, it's just 162 megayears actually. So my collaborator Shoshana Byrne-Mamahit is actually working high temporal resolution zoom-in simulations of galaxy mergers, and that's one of the things that I'm hoping to be able to use to increase the precision of the coalescence. But with Illustris, that's the best that we can do.
Okay. Do we have more questions? Rogério, screen.
So, hi, Leonardo. So thanks
Hey.
for the very nice talk. So regarding the AGN fraction, so you are showing that it is lasting something like 500 million years. This is much more than a duty cycle of an AGN, okay? So I'm wondering if there is a way of measuring if they have turned it on, let's say when there was this coalescence, turn it off and turn it on again, like in this period of time?
That's a very good question. For the agents, the problem with the simulation is that we are limited to the subgrade physics, right? So there's like some subgrade physics that it turns on and turns off. And in the observations, the time resolution of our classifications are very sparse. We can do the time slicing now, but it's very sparse. So I don't think we can. I mean, I'll be happy to hear from you if there's any things in the observations using the survey large area data that we can to differentiate two types of agents, to maybe say that for example for the ones that are the excess at 1 gigayear, the two excess at 1 gigayear, 0.5 1 gigayear, we can say that okay, that's the agent I actually turn on during coalescence, but it turn off and then turn on again. That will be, if there's a way to do that, that would be great to do. But currently we didn't do that. There's a lot of stuff that we did in this paper for the agents. For example, if we look at the broad line agent, there's no signal in the pair phase because everything is obscured. But once you go to the post-merger phase, you can see the dust basically is clear, right? You can see it. So there's a lot of things that we did about the observability of the agents in the paper. But in general, I don't think with the time resolution that we have here and the limitations from the simulation, I don't think we'll be able to do that. I mean, but I'll be happy to hear from you if there's anything that comes to your mind.
Okay, perfect. So I'm going to drop you an email.
So I have a final question about the unions. So
Yeah.
can you go back to all the unions sub-surveys that you mentioned? And I had a doubt. What is CIS?
CIFIS, yeah. Sorry.
That one.
Yeah, so CIFIS, so this is a nightmare actually, because this is a decision that the unions group had. So originally the CIFIS was the Canadian France imaging survey, right? So that was the survey of the R band, the U and the R band of the northern sky. And then that became part of unions. So the R band is CIFIS. When we're talking about unions R band, we are talking about the Canada France imaging survey, which is now they want us to call it just unions R band. We'll have to drop the CIFIS nomenclature.
Got it. And so I understand there's many surveys that end up becoming part of unions, and one of them is NGVS. Is that going to be also made public soon?
I'm not entirely sure, but I think yes. So I think Stephen Gwen is the person doing all the reduction and preparation of the data for the CFHT data. So anything from CFHT that is part of unions, I think is going to be released.
Okay.
It was supposed to be released last year actually, but they delayed a little bit. But I think I think they are converging to release it very soon.
Okay, so if there's no more questions, let's thank Leonardo again.
Okay.
next time, let's do it in person.
Yes, thank you. See
Bye-bye.
ya.